Hello everyone. Rohan, do you want to get started?
Yeah, sure. Hello everyone. Good morning, good afternoon, and good evening to whichever part of the world you are in. And a very warm welcome to each one of you in today's live session. For those who are new here, we are DeFi, a global AI community started with a vision to educate and build AI to solve meaningful problems. In our endeavor to constantly give back to the community, we are regularly conducting boot camps, live workshops, and industry sessions, and also datathons and other events. Today's session on building credit risk models is organized in collaboration with our very own community partner, Databus. We also have Supreet, who is a co-founder of Databus, and we thank you, Supreet, for making this session happen. I now pass on this to Supreet and to take it forward. Thank you very much.
Thanks, Rohan. Hi everyone. I'm Supreet, and currently I'm an AVP at Morgan Stanley. But outside my work, I'm also the founder of DataBuzz. It's one of its kind volunteer-driven community aimed to engage people who want to pivot in the field of tech, data science, AI. So we conduct these sessions in collaboration with these amazing communities, DeFi, who are on a similar goal to educate everyone and provide you with the thorough of knowledge on all of these interesting topics. And this is our fourth session. Three have been very successful, and I'm hoping this will be a blast as well with all your support. The community has been very active by, providing a lot of questions, chatting with us. So please do that. Be active in chat, and we'll respond as soon as we can. So now I will call my speaker, Dhruv, who will introduce himself, and I'll let him take this session. Hey, Dhruv.
Hey, hi Supreet, how are you? Long time.
Hello. Hey, Dhruv. Okay, Dhruv. So why don't you take this, introduce yourself, we'll be in the background, and continue with the session.
Okay. Thanks Supreet, thanks Rohan. So I'll just start by giving a brief background about myself. So my name is Dhruv. So I currently live in India, Mumbai. And I have been working, so I'm an electrical engineering graduate and I have been working for the past 6 years. I started my career as an investment banking quant analyst. I did that for around 2 or 3 years. After that, I got really interested in data science and machine learning. I didn't have a lot of idea about what really does it mean to do data science and machine learning, but I just got excited. I think like a lot of people at that time. At that time, there were not many communities like DataBuzz and DeFi, which I think is great that we have now. That people who are just interested or wanting to venture into data science and machine learning, they can actually be part of these communities and get a better sense of how to do that. So thanks, Supreet and Rohan, I guess, for putting everything together. So coming back to me, so I moved to a data science role at Protium, which is a fintech company. I joined Protium. So there's a fintech company based in India. I joined Protium just when it was starting, so we had not even incorporated yet. So um, I was the founding member of the data team, and the data team comprised of data scientists, data analysts, and data engineers. So I started out there as a senior data scientist, but essentially had to do a lot of data engineering, data analysis, and build all the infrastructure from the ground up. 3 years, so I was there for close to 3 years. Most recently I was the director of data science and risk there, and it was a great learning experience for me because we went from zero to a AUM of around $500 million within those 3 years, and I was very structurally important to that transition. And I got to learn a lot, especially since I didn't come from a fintech or a data science background, so I had to pick up a lot of stuff. A lot of the stuff that I actually picked up was fairly non-technical, in the sense that obviously I had to pick up how to train models and how to clean data and stuff like that. But I also learned a lot of stuff that you really can't learn online or through courses. You really have to be there and do that in order to learn, and which is what I will try to share here today, so that people get a better sense of what it feels to be a practitioner in this field, which takes much more than just technical jobs, which are also very important. But like there's a bunch of other stuff that we also need to focus on as data scientists, and I hope to share that with you guys. Okay, I think with that very long intro, I think I'll just start with what I have planned. So today we're going to talk about credit risk. So for any fintech or bank which is into the lending business, so lending money to borrowers who need money, credit risk is very essential. And credit risk, to put it very simply, is the risk that when you give money to someone, they will not pay you back as agreed upon. In very simple terms, that is what credit risk is. And if they don't pay you back, that is called in industry jargon default, that they defaulted. So if you are into the lending business, obviously the risk that something like that happens is very central to how you run that business, right? So credit risk is the central, is sort of at the very core of how fintech, a lot of fintech companies and banks who involved in the lending business are there. And essentially, the risk actually boils down to how much risk you'll have, boils down to how good are the decisions that you make in terms of who you give a loan to and who you don't. And so, in order to control risk and in order to sort of take good calls in terms of risk, you need to have really good decision making, right? That finally it comes down to who are you saying yes to and who are you saying no to among the people who come to you to get a loan, right? So this is as an industry, credit and credit risk is probably 2000, 3000 years old. It's as old as money itself, right? And it's always been there, right? And it's not always it hasn't always had data scientists. So this is sort of this infographic is sort of my attempt at highly simplifying a trend that initially, like probably 100 years ago, people used to have a lot of documents and files on paper, and these people who are employees at any bank or fintech organization, these guys used to take decisions based on their understanding heuristics, and obviously they were very professionally trained, they had a lot of experience, and they use that experience to make good decisions about who to lend to and who to not. um, Very recently, after sort of the information age kicked in, there was a lot of data that was available, structural data that was available with the credit bureaus coming up, which maintain a central digital repository of all loans that have been given within a certain country. There has been a lot of digitization on that front, and now a lot of places have sort of machine assisted credit assessment, where people do make the final decisions at a macro level, but a lot of small decisions and small sort of calls are taken by machines. But at the end, there's still a human who keeps check of the whole system. So that's the middle sort of image, and the right is obviously the illusory AI-driven system where humans are not doing nothing, but they're just putting their feet up on the desk, and a computer is just taking care of everything. So none of so this is. I mean, it's very simplistic to say that this is how it's evolved, and we are here or we are here. The truth is, we are at everywhere the same place. I know organizations that still deal with paper files and take decisions in that way. I also know organizations who are completely automated. So even at a given point in time, a lot of organizations are in different states, right? And but overall, the trend is towards automation, towards automated decision making, and that's good news for data scientists in general. But obviously, not all organizations are at the same point in the curve. So as a data scientist, I think the point I want to make is that you need to be really when if you're trying to become a data scientist in the credit industry, you need to be very careful about what sort of organization do you want to work with, and you want to make sure that as a data scientist you'll have a lot of impact there, right? So organizations which operate at a very high scale and have a lot of information digitally available can actually leverage data scientists to make better decisions, and people who don't have that might do a little better with data scientists, but they're not going to make a lot of difference there. So that's sort of a that's sort of an assessment that every data scientist should do, right? Then this is just essentially why use models instead of people. Why are we going in this industry? They're cheaper, they're faster, they don't have human bias and variance. Like humans are biased, and their decisions can vary a lot. Given the same situation, they might take a different decision another day, right? So that's why everybody's sort of moving towards, model driven decision making, even if not completely automated. At least some parts of the decisions are taken by the model. And we've seen a trend where all sorts of big fintech and organizations and banks have actually seen and realized very high ROI from building models. And so models in the credit industry are called scorecards for some reason. I mean, it's sort of completely because, I mean, I don't know why that is, but that's just like a legacy of someone who once called this a scorecard, and that's continuing on. So scorecard is what a model in the tech industry called a scorecard in the credit industry. So this is called scorecards, right? So for a while, developing and maintaining scorecards has a very high positive ROI for all financial institutions. So that's good for data scientists because they will need a lot of data scientists to actually develop these scorecards. And things that have contributed to this trend is like available of very high structured information digitally. A very big contribution of this is from credit bureaus who actually maintain all the formal economy loans that are given formally in a central ledger. And not just that, they also keep a track of how that loan is performing. So if I take a loan from any bank in India, central bureaus are going to track that information, and then are going to track how I'm doing on that loan. So this is a very rich information source that is available to every lender digitally within seconds and for very cheap. This has actually highly accelerated the process of digitization and automated decision making. Right. So that's sort of the overall macro trend. We will actually build a model today, but before that, I want to sort of gloss over something that I think is very important. It's not covered a lot, but it might be slightly boring, but I wouldn't feel right if I didn't mention this. Like, um, as data scientists, we're very fascinated with models and we all want to build models, but it's very important to actually know what is the objective from an organization standpoint. What is the objective that we're trying to solve? So this is a conversation that's actually, I mean, I've seen this conversation happen a lot of times. So let's say that there's a data scientist and so data scientists don't work on isolation. In most of lending organizations, the final risk decisions are made by someone who's a risk head. He's almost never a data scientist, like, but he knows what the value the data scientist can bring. But essentially you're working for the risk head, and anything that you do has to create value for him, and he has to agree on the value, right? So let's say that you're a data scientist and you come to the risk head and say that we have a mortgage lending business. A mortgage lending is essentially lending secured lending where there's a collateral, which is sort of a house or a property, right? A physical property. So that's mortgage lending. So there's a data scientist who's very excited, who is said that we have a mortgage lending business where we take decisions about who to give loan to, who not to. I've actually trained a model using credit bureau data. It has a very high AUC, and it's like in decision making, it is at par at what our people are doing. Like the people who are making the decisions, my model can make the same quality of decisions without really without taking so much time, and it's so much more cheaper. But then the risk head says that, okay, you've built this model, and okay, the performance is like the AUC is 0.7 or whatever, but mortgage loans are very complicated and a lot of structured information that you've based your model on. There's a lot of unstructured information and a lot of subjective information that comes in, which we have to take into account, which your model cannot take into account. So I cannot really trust the model. And secondly, you can't really use a model for the complete decision making because there's a lot of paperwork and there's a lot of manual things, like you have to visit the property which has been mortgaged and stuff like that. So you need to have people there. You can't really automate this, right? So the data scientist is obviously disappointed in terms of can you really not use the model that we built? And then the risk head says, just to placate him, that no, you can use the model. We'll use your model output into our decision making and stuff like that. But obviously, it's not going to be automated, right? And for a data scientist, that's pretty disappointing that their score is their model output is just going to be a parameter in a very long process of manual decision making. And the sort of the conclusion from this is like always make sure that whatever you're working on, it's actually, if it turns out well, it actually can create impact. Like in this case, for a mortgage, most of mortgage lenders have scores there, but every decision, because mortgage lending is a business which is highly regulated, and every loan is relatively larger, right? It's not like a buy now pay later where you buy an iPhone or buy a phone for a short amount. It's a large amount, so people are always involved. There's always a lot of manual process, so you really can't automate that. And it's sort of a conventional industry, so it's very important to understand where you're operating and where the best bang for the buck is, right? So that aside, like the types of objectives generally you have in the credit industry for a data scientist is one of largely these three. One is you improve productivity, and this is sort of cuts across all industries. Is, there's existing process that's going on, so there are people who are looking at some parameters, making decisions, right? And you feel that these decisions are not that hard to take. You should be able to train a model to make the same decisions, right? So what you're actually doing is just increasing productivity, saying that five people take 100 decisions. Why don't I train a model which can take like 80 of those decisions, and 20 decisions which the model is not sure of, that one person can take. So you have increased the productivity where only one person is needed to make 100 decisions, right? But you're not necessarily improving the decision making. You're just improving productivity, right? So that's one of the objectives. The second objective can be control credit risk. So you realize that a lot of the decisions you have been taking have been wrong. So the people you have been giving money to, they're not returning it back. So you really want to control credit risk. That's where you want to make models which actually beat the current models or the current decision making process in terms of making better decisions, right? So now you need to really create a model which, it might make people productive or unproductive, but you really need a model which can make better decisions, right, than what is already happening. And the third kind of models is sort of, you can create models for all your customers who you have already given loans to. But even after giving loans, a lender's responsibility doesn't end there. He has to continuously track how people are doing. Are they making payments or not? Given their current activity, what is the risk that they're carrying? And so these models are more from a monitoring standpoint, and they try to estimate, on a portfolio level. So on an aggregate level, what is your risk, right? So that's sort of a few objectives then it can be there, and the approach for each of these objectives is going to be very, very different, obviously, right? So with that aside, I think we'll move towards the more exciting part, which is actually training a model, right? So here what we're going to do is, the risk head has come to us and said that, I have a certain number of loan applications coming in. I just want a model which can either approve or reject, right? I just want a binary model which can tell me which cases to approve and which to reject, and the model's word will be final. There's going to be no manual process, right? So this is sort of a very ideal conversation to have with the data scientist. The data scientist is going to be very happy, right? So the setup here is that people are going to come in, they're going to log certain information, which is the application information. Using that information, we'll have to assess what the credit risk is. We have a lot of historical data, that given these application sort of variables, what was the actual loan performance? So whether did he default or not default, right? We already have this data, so we can frame this as a supervised binary classification problem, right? And we have the data to actually frame it as a supervised binary classification problem. Now, in generally, I would have stressed on how to create this data set. There are a lot of catches in terms of how to create a target variable. What is the target variable? Till now, we've just used the word default in an abstract sense, but you need a very clear definition of what default actually means, right? So there can be a bunch of definitions of what does it mean to default. Like if I miss even a single EMI, can you call me a defaulted customer? Or you have to miss like consecutively 2 or 3 EMIs there, that's when you say that, okay, this guy's really defaulted. So there's a lot of variations here, and there is a lot of work that goes into creating features. So all the input parameters that you have in your application, those need to be sort of engineered. You really need to understand how they're going to impact your credit risk, and you need to either combine them, aggregate them. And you need to spend a bunch of time thinking about, how you can squeeze the maximum value out of that. Sadly, though, I don't have the data to act that represents reality, and I just have a very clean sort of data which I picked up from Kaggle. And so I'll just show you. This is a very popular Kaggle competition in the credit risk domain. And this was probably the only one for a while, but now you have like a couple more from Amex and stuff. But this was the model for a while. This is a home credit, which is actually a fintech. It's a bank which does essentially provides credit for people to buy homes, right? And they have provided us a data set in which they have application variables, and they also have a target variable, right? So let's just have a look at the data that they've already provided us, right? So I've already downloaded this data set. Yeah. So here is our target, right? This is around 300K observations, right? Which is a lot of data. There's enough data to train a really good model, right? So anything above, so this is also a heuristic that I learned pretty because I was part of a organization which is starting from zero. We had to really get a sense of after how much data do you have, can you start building sophisticated models, right? So unless you have like more than let's say 10,000 or 12,000 observations, it's really hard to train any modern machine learning models like XGBoost or stuff like that, and really see them outperform simple techniques like logistic regression, right? So here we have around 3 lakh data points, which is more than enough to build like, the most state of the art algorithms in credit risk at least, right? Now we have the target, and we have 120 features in there. Now the sad part is that they have not really provided us a dictionary, a data dictionary, to tell us like what each feature means, which actually in the real world that's pretty important. You can actually just by looking at the names you can figure out, okay, what means what. But and we can sort of work with that, but generally it's pretty important what each feature is, and you really understand what each feature is. You spend a lot of time there so that you can actually create features and create new features through feature engineering. But we're going to skip that part because it's not possible to do it here, and we don't have a data dictionary. But essentially this is what we have 120 parameters that were captured for a loan applicant at the time that he made the application. And then you have this target which tells us that after he got the loan, in a certain time period, did he default or not, right? And that's this indicator, right? So you have people who have defaulted, and you have people who did not default, right? And you have around 3 lakh observations. So if you want to look at what sort of is the distribution for the target. Right. So around 8% of our whole data set are defaulters, right? That's I mean, that's a high number, but you really can't say. Like, people have different default rates across different segments. So in sort of mortgage loans, like if you are taking a loan to buy a house, the default rates on those loans tend to be very, very low, because if you default on the loan, they'll take your house, right? So people don't tend to default on those. But typically loans where which are unsecured, so you take a loan, let's say just you take a personal loan, and there's actually nothing. If you don't pay back, they can't repossess anything of yours. There the default rates tend to be higher, but here it's 8%, right? So that's that. So you have this feature set and you have the target. The first thing that you generally want to do is you want to get a sense of, given all these features, what is sort of, for each feature, how strongly is that feature related to my target, right? That's generally the one of the first things that you want to see, so that you can, we have 120 features. We want to filter out as soon as possible. We just want to filter out stuff that's just not going to work, right? Some things like maybe, gender has no correlation with whether they'll default or not. So we'll get that out of the way, and we'll also get a sense of what's really important, right? One of the popular measures, especially in the credit industry, is something called the information value. So the information value is sort of the equivalent of correlation. So you measure correlation when you have like a continuous target, and you want to measure the strength of association. The information value does that when your target is binary, right? It's actually based in information theory, and I've put up a link here if you really want to understand how information value is calculated. But for now, I think we'll just assume that it's something. If it's more, that means there's a stronger relationship between a feature and the target, and if it's lesser, then the relationship is weaker, right? And I'm using a library called opt-binning. It is one of my favorite libraries, which can actually calculate this pretty fast for all the features. So we're gonna run this. By the way, I'll actually, I think I'll take some questions at the end. Yeah. Yeah, I will share all the code and the data with Supreet and Rohan, and they can share it with you guys. I also put up a GitHub link, right? So yeah, we've already run this, and now what I'm looking at is each feature and what is the information value, which a higher number is a stronger association. Generally, the rule of thumb with information value is 0.05. If something is greater than 0.05, it's generally a good relationship, like it's a strong relationship. So we can see that there are a few relationships that are very, very strong. So exit source 3, which we don't know what it is, but it does seem that it's very highly correlated with our target variable, which is default, right? And this is just the top 10. Uh, we also have, let's look at the bottom 10, where you essentially have an IV of 0, which means that there is, in this data set, there is no correlation between these features and the target, right? And if you look at the distribution of IVs, most of them are below 0.05. Only close to like 10% of them are greater than 0.5. So this is just the percentile distribution of the IVs, right? So what we want to do by measuring these trends is we just want to do away with all variables which absolutely have, based on the data, no relation to the target. We don't want to unnecessarily remove variables. We want to keep till, so we're not into the model building part yet, but till the model building starts, we want to retain every feature that can even create a little bit of value, right? But we also don't want to use unnecessary compute, because these algorithms can be hard to train, right? So we just want to remove variables which are like, which will like high degree of confidence we can say they'll create no value. But generally don't do away with features which even have a slight value. Let the model figure out whether it can use it or not. That's my approach, right? Let the model figure out, because modern machine learning algorithms are very robust to noise, and you can cross validate and stuff like that. So I generally tend to leave those decisions of skipping variables to the model, but I will remove everything that's obviously zero IV. All those stuff I'll remove just to reduce the compute that the model will use and reduce the noise a little bit, right? And we're also not overly obsessed with collinearity. So a lot of approaches you'll see, you'll have correlation matrices being computed, and you want to remove highly correlated features. That stuff is fine if you are using linear regression, where the estimates for your coefficients and your overall regression can depend on whether you have highly correlated features. But we are going to use tree-based methods, which which are really robust to collinearity. So we're not overly obsessed with that, right? So we've looked at sort of one number which measures the strength, and we've seen relatively which variables are stronger. Now I also wanted to look at one of the variables and see after you sort of figured out that okay, these 10 or 12 variables are pretty important, then you look at the actual relationship, right? The actual relationship with the target variable, right? So this is only a number which gives you the strength of the relationship, but you're not really sure what is the nature of the relationship, which is also very important. If you don't understand the nature of the relationship, generally you will not use a variable in the model, even if you feel that it's very strong. So day's birth is essentially, so I looked this up on Kaggle, and day's birth is essentially sort of the age for the applicant, right? And a negative number means a higher age, and like the as you go towards the positive side, it's a lower age, right? So that's just how they've encoded the variable. So you can see, so this table can be overwhelming, but generally just look at the bin, right? And the event rate. So the bin is essentially for this day's birth variable, which is a float. Uh, this this package of binning has actually broken it down into 20 bins in an increasing order, right? So increasing order in this number means decreasing order in age. Okay, so as you move down, your age actually decreases, right? And the second thing you look at is the event rate. Now, the event rate is actually the default rate. So within this age bracket, out of the total people that are there, which is like 115,500, what are the events? So events is actually the defaulters, and that event rate is actually 4.3%, right? Which is quite low because overall we saw it's 8%, but within that age bucket, this is actually 4%. And you see, as you move up, so as you decrease the age of your applicants, the event rate keeps going up, right? So this is a relationship that is very intuitive to people who have actually done any credit risk modeling, is that age is actually a very strong predictor of credit risk, because the general trend is as your age increases, your earning capacity increases, and the more your earning capacity, the better borrower you are, and the lesser likely you are to default. So this is how. So this package actually allows you to visualize the relationship in this fashion, which is very important. So in an ideal scenario, I would go over every variable that I want to feed into my model and see if that relationship makes sense, right? Given your intuition as a credit risk person, does it make sense or not? And something that doesn't make sense, you generally don't use that, even if the association is very strong, right? So we've here selected all variables which had an IV of greater than 0.05. Assume that all the relationships make sense, because the truth is here we don't even know what a lot of these features mean. So we can't do a lot of exploration on the individual feature side. So let's just go ahead and say we have like 11 final features which are slightly correlated, like at least reasonably correlated with the target. And let's move on and say that, okay, these are the features we've selected, and move to building models. Now, the model that today I'm going to train is like a light GBM model. But in general, tree-based models are the bread and butter of the credit risk modeling industry now. There have been a lot of people who try to work on neural networks and stuff like that, but tree-based models have generally outperformed all deep learning in sort of neural network based approaches for not just credit risk, but all sort of tabular data sort of problems, right? So a lot of innovation that's happened on the deep learning and all that side is on non-tabular unstructured data, but on structured data, tree based methods have uh, performed equally or better than neural network and deep learning based approaches. And the advantages you have over sort of a regression setup is like the scale invariant, so you don't have to change the scale of your variables, you don't have to do any feature transformations, they're robust to multi-collinearity, you can have highly correlated features, that's not a problem. It's robust to outliers, so linear regression techniques are very sensitive to outliers, like one outlier can throw off your entire model. Tree-based methods are naturally very robust to outliers. They've been proven to be state of the art for tabular data modeling, right? And specifically, I picked light GBM here because it inherently can handle categorical data, which XGBoost or random forest, they need sort of a one hot encoding before you go in there, but light GBM itself, the implementation handles it. So just for the sake of convenience, I would use that. Generally, I would either go with an XGBoost or a random forest, but a light GBM actually is very good for very fast iterations and quick implementations, right? So this is where we're training the model. So there's a lot going on here. I'll not actually go very deep into how the model algorithm works and how the model training works, right? I think all that is covered pretty well in literature and online. So we're just gonna quickly gloss over this. So there are some hyperparameters for the light GBM that I'll tune using a simple grid search, right? And yeah, and I'm feeding it the selected features. So the selected features for 11 features that we selected based on IV, right? And let's just, so these are the features, these are the feature types. So you have like 3 categorical features in there, and the rest are all numeric features, right? And let's just run this. Now, when it runs this, since it's doing a grid search, it'll look at all these parameters for the light GBM, and it will train models for each of these parameter combinations, and it'll return the best model. So in the end, we'll have sort of a model that has the best hyperparameters for our training task. So this can take a little bit of time. Yeah, but no, it's already done. Right. So now let's look at, so the best sort of light GBM model that we had these hyperparameters, and the metric that we are displaying here is the AUC. So we'll talk about AUC a little bit later, right? And so it's, let's say, 0.73 or whatever, but let's say that the AUC is high and we are happy with the model. One thing that we can now look at is feature importances. So the model has learned some features. We've given it some selected features, and the model has used these features. But some features are obviously more important to the model, and they were more crucial in the training process than others. And a ranking of these can be found out by looking at feature importances. So each algo sort of has its own thing of how to calculate importances, and you can look at these and say what has the model considered valuable. This can be very different from IVs, because IVs are standalone relations with the target, and this is what the models actually learned, right? So you can actually see that the age actually is a very important. It had a high IV and it came out to be very important. But days employed is something that probably did not have that high of an IV. It did actually, but it was still less than all of these. But in the model, it comes out to be very important. So this actually happens when the model will all the variables interact. There might be some that actually don't have a lot of strength directly with the target, but when used with other variables, right, they actually become stronger. And that's why these results can be very different, right? So the AUC is what we used here to judge the model, but especially in models where we're trying to do an approve reject decision, which we are trying to do here, right? What you also end up looking at, which is very important, is sort of the recall at, let's say, K%. And so what that means is, if you were to reject, so let's look at this table. So we'll just quickly, so the AUC is fine. So the AUC just tells you generally is how well does your model do in terms of ranking the defaulters higher than the non-defaulters. It's a general metric to figure out how good a classifier yours is, but it doesn't like, is a 0.73 AOC good for my use case or not? There's no answer to that, right? So it's good that it's a high AUC. So that means, so one interpretation of AUC is, if you randomly pick a defaulter and you randomly pick a non-defaulter, what is the probability that your defaulter will have a higher score given by a model than the non-defaulter, and that probability is actually the AOC. So in that sense, it generally gives you a general sense of how well your model is distinguishing between defaulters and non-defaulters, but it doesn't tell you if you can use it to approve or reject and stuff like that. So for that, what I usually do, and I've seen a lot of people do this, is you create a table like this, right? And what this table actually tells you, so the table breaks down the whole population, population that I've already done my scoring on, I've run the model on, and I have the target as well. So let's say this is like the test population which I held out, right? And what it's telling me is that, so this is the 10% of the population which had the highest probabilities of default. So according to my model, these are the 10%, the worst people, the worst 10% people, right? And the default rate here is 31.46%, which is very high considering the average is 8%, right? So if I take the second bucket, which is like the second 10%, which are like worse than everybody else, but like better than these guys, there the default rate is 17.8%. When you look at a table like this, you can actually make decisions as to where do you want to put your decision threshold, right? Because we have trained the model, but the model itself is not what the ask is. The ask is to have a system that can either approve or reject, right? So we have to figure out, on top of the model probabilities that we predicted, what is the threshold that I'm going to apply, and say that if the risk of default is higher than that, I'm not going to approve it, I'm going to reject it, right? So let's say I choose this threshold. So I say the top, these two people who are like who have greater than, let's say, 0.11 probability of default according to my model, I'm going to reject both of these guys. So 80% people will pass, 20% will fail, but these 20% have really high default rates, so I'm going to avoid these guys. but I'm okay with taking this risk, right? And this is a decision that you can't take as a data scientist. It's something that you have to discuss with sort of your the risk head and the business head. But this is the sort of metric that you will have to show them. You can't tell them the AOC is high, but this is what you can tell. You can say that, these are the decision choices that you have. You can reject 10% and be okay with keeping these people. You can reject 20% and be okay with keeping these people, right? So this is how you sort of communicate and actually create a system out of the model, right? So the model itself is only outputting probabilities, but your job is to create a system on top of the model, which has to have a decision boundary, right? So that's sort of it from my side. The last small point that I will make is on explainability, right? This is a very important thing in finance, in general, and also in credit risk. Is models, especially machine learning models, are not really very explainable as compared to regression models, where you have like coefficients for every feature and you can actually figure out how each feature is interacting in the model and how it's behaving. So one of the things that but we are making a lot of progress on that front from a machine learning standpoint. And something that I've seen used widely now, especially in the credit risk industry, is shapely values, right? So there's a package called SHAP in Python, which you can use, right, to figure out shapely values. Shapely values, I think I'll link a resource where you can get started. Essentially, what shapely values do is, for any model, they break down every prediction as a sum of contributions of each feature. So if you have three features, let's say age, income, and number of children, right? When you use a tree-based model, the output is, let's say, zero point 0.5. The probability is zero point 0.5 for default, right? But how do you attribute that zero point 0.5 to what came out of age, what came out of number of children, and what came out of income? Shapely values actually does that. It can break down each prediction by what was the individual feature contribution, and it has a lot of nice properties, and it is model agnostic, so you can use it with any model. It does not depend on the model, right? So for example, here, um, we're looking at a specific case, right? So let's look at this case. So this is just like one application, right? The index is 780, and the probability of default that we are predicting is 0.74. Okay. Now this 0.74, how is it broken down into all the 11 features that we've used to make this prediction, is what you can see in this plot, right? So this is sort of a fancy plot, but essentially what it's saying is that, so this gray line is the average prediction, which is sort of the average default rate. So if you don't know anything about a person, your default rate prediction is going to be what the average default rate is, which is 0.08%, right? So this is the average line, and this is each feature's contribution towards changing what the average prediction would have been, right? For example, the ext source 2 actually causes the prediction to become positive. So whatever the value of ext source 2 is, which is 0.673 for this person, right, for this specific person, that actually makes him slightly higher risk than average. But the ext source 3, which is 0.235 for this person, compensates for that, and the average risk comes down to 0.74, which is actually lesser than average, right? So each feature is contributing in its own way, and the sum is what finally comes down to your prediction. So this is a very, very good way to not just understand as a data scientist what your model is doing, but it's very, very, very helpful for you to provide this feature to your users, where people will be able to understand that why the model is predicting something like that, and which are the features, which are the major contributors for that, right? So this is obviously very, very interesting. I'll link on shapely values and the SHAP package, and I think this is going to be pretty important from a credit risk standpoint. Almost every sort of credit risk shop uses shapely values in one form or the other, as far as I know, right? So yeah, that's on the explainability side. There's a bunch of stuff that has to happen post deployment to figure out whether whether your model is still working or not. There's data drift, concept drift, and reject inferencing that you need to do. But I think that's a link to a resource which will help you on that. But in the interest of time, probably we will not cover that unless we don't have any questions. In which case, I can cover that.
Yeah. Hey, Dhruv, I think we have a lot of questions. So I'll just add Rohan to stream as well. And we just, first of all, thank you for the session. It was really great. And I think everyone enjoyed so much that you have plethora of questions here. So
Yeah.
let me remove this. Okay. So now the first question is, how reliable is the application data? How much noise it generally has?
Yeah, that's actually a great question, and that goes into sort of what real world data science and machine learning looks like. In this case, obviously, the application data has been cleaned and provided to us from by Kaggle and Home Credit. But generally, the application data, um, depending on what sort of an organization you're in. So let's say you have a website where people can come in and apply, right? In that case, what's going to happen is all the transactions, all the interactions that the borrower has with you are completely digital, and that information is stored and it's sacrosanct and it's immutable. So you generally do capture every interaction, all the variables. But let's say you are a company, you sort of have branches in there, you have a lot of branches, and people actually come into your branches and they talk to people and they submit their application. Then an application has to be uploaded into a system and stuff like that. So I've seen both of these things happening. In the second case, you will have to really figure out which are the fields that you can actually rely on, because in the end, if there's a human involved, there's a lot of chance that people are going to take shortcuts and not fill in the right data, or there might be a lot of missing values. Let's say you have an application where the person in the branch already knew that this is not going to get approved, so he doesn't even input that data, and that can cause your model to be biased, right? So uh, the application data will be really noisy, but you can't really isolate yourself from the data generative process. If the data generative process is a website, then you can be much more safer. But the data generative process has a human involved, you really have to understand what are his incentives, and in which case is he more likely to mess up.
Great. So the next question is this: can you explain on reject inference modeling and process?
Okay, yeah, this is something that's very fascinating about credit risk is, and this is a very subtle point, but a very important point is reject inferencing. So let's say that we actually built this model that we already had, and I actually started rejecting 20% of people based on this model. Okay, now 1 year has passed by. I want to figure out that, okay, I when I trained this model, I calculated my AUC, I calculated some other metrics. It would be good if, after 1 year, you can really, because it's been 1 year, you've already been using this model, people would have defaulted, not defaulted. So you actually want to reassess and see if those numbers still hold up, right? But the challenge is that because you rejected the bottom 20% of the people, you only end up giving loan to the 80% of the people, and you only have data about these people, right? You rejected these guys, so you don't really have data about them. So you can't really know if this prediction of yours, like you were saying that the bottom 10% is going to have a 31% default rate, right? How can you verify that? Because you never ended up giving them a loan, right? So then you can't really know if your model is working or not. And that is actually that's a very subtle point, but it's very important. And the solution to that is, most of the times it's provided by credit bureaus, right? So even though I end up rejecting 20% of the people, if somebody else gave them the loan, right? Let's say a similar loan, the bureaus will have that information. And at the end of 1 year, I'll go to the bureau and said, I rejected these guys. But if somebody else gave them a loan, can you tell me if they gave them a loan? And can you tell me the performance, whether they defaulted or not? Right. So now what you're doing is, on your rejected sort of cohort of people, you are figuring out what that performance was, and you're trying to infer whether, the sort of predictions you made on those people were right or not. Right. So this is one of the cases where your prediction actually changes the data distribution, and then the distribution that your model is running on is no longer the same distribution that you trained your model on, right? So yeah, Jatin Devi saying great session. Thanks, Jatin.
Nice. Okay, so the next question is, let's take this one.
IV is more of a linear mapping, right, than a non-linear approach for estimating feature strength. So IV will capture all sorts of relationships. They don't need to be linear. So maybe I'll just sort of go into how it's calculated. So how IV is calculated is you actually break down all your features into bins. So your numeric features, you sort of break them down into quantiles, and your categorical features are themselves. So here we have a categorical feature which is like occupation type, and here you break them down into sort of clusters of, so this is cleaning staff, sales staff, accountants, high skill tech staff, right? And you sort of see what for each bin you actually have an estimate of IV, and what that IV tells you is that within that bin, how different is that bin from average? So if in this bin the event rate is only 5.5%, right, whereas the average is 8%, right, this bin significantly has a different relationship, has a different behavior than average, right? And for each bin you can actually figure out, this difference from what this bin is doing versus the average. And the more that difference is, the stronger the feature is in terms of predicting what the default can be. And you aggregate over all bins and calculate an IV. So I will link what the exact calculation is, but you are actually not assuming linearity. You actually break stuff down in bins. You assume that the effect of the feature is uniform within that bin. That's an assumption you're making, that in one bin the behavior remains the same. You can't really further break this down. That's an assumption that you make. But then if you make that assumption, any relationship can be captured, doesn't need to be linear.
Yeah, makes sense. So let's take this as next. How do you choose the random state of random forest model? Is there any technique?
So you can choose the random. The random state is essentially just an integer, and you just choose it so that every time you run a model which is not deterministic, you get the same result. You have to choose that sort for every like XGBoost, light GBM. You have to do that. That is not what the random in random forest means. The random in random forest essentially means that in a forest is like a bunch of trees, and you're training a lot of trees using a random subsample of your training data, right? So that's what the random in random forest stands for. It has nothing to do with the random state.
Yeah. Okay. So one more that we have is how to start with a cold start problem where you don't have a target. Only the user's PI information. This is a good one.
That is actually an excellent question, something that sort of I have dealt with. The short answer is, I mean, you really can't do a lot of stuff if you don't have any data.
Yeah.
Even if you have PII information, right? Even if you do have PII information, and getting information from the customer is not a problem. It's getting the performance. By definition, to get credit risk performance data. So home credit already gave us ones and zeros, right? But what did they have to do to get those ones and zeros? They had to actually give the loan, and they had to monitor the loan for a year, 2 years, and actually see the performance. So what you don't have when you actually start, you start sort of you don't have a lot of data to start with. You don't have a lot of target variables that you have. You only accumulate your target variables over a long time. So how generally organizations deal with that is you actually go to credit bureaus and tell them what sort of customers you're going after. Those bureaus can segment on those customers within their database and create models for you, or sell you data and you can create models on them, so that you sort of have a lookalike population on which you already have your target variable, and you can create models. But in order to create models from your database, you have to wait a while so that the performance actually starts showing, people start defaulting, and then you get this thing. Generally PI information is not used in models. Like, there is very high regulation on what is the stuff you can use. For example, you can't use gender, even if it might come out significant. You can't use like name or caste and stuff like that. You can't really use that. Even age is something that is debatable whether you can use it or not, because the person cannot really control their age, right? So PI information, using only PI information, the only really good indicator you can get is from geography. There is a very, especially in India, there's a very strong correlation between credit risk and geography. There are certain geographies where you know that there is a high risk of default because of the nature of industries, the nature of commerce over there is such. So the geography is something, this is the only, probably the most, the strongest thing that you can get from PI and that you can legally use. Apart from that, from PI, you don't really find a lot of value coming in.
Awesome. So we are getting some thank yous this session. Rohan, do you have any last comments to add before we end?
Yeah, of course. Thank you very much, Dhruv, for a really wonderful and insightful session.
Thanks.
Normally, we ask this to our speakers, like, how did you break into data science field? And that would be really helpful for our aspiring data scientists as well.
Yeah, no, that's something that I also wanted to talk about is because, as I was saying, when I was doing this, you guys were not there, sadly. You guys had not started doing this. So it was really hard for me. But what did work for me was I used to sort of, I used to be very active in writing code and building models and putting stuff on GitHub, right? That sort of, and sharing it on LinkedIn and stuff like that, that gives me sort of a feedback in terms of, because it can be a pretty thankless process initially for people to want who want to get into data science. They will not see any validation, and because in data science, especially credit risk, experience is highly valued. People want people who have experience, right? And somebody who does not have experience is generally somebody that, even if they're pretty smart or they know their stuff, people don't want to take a bet on that, right? So I came from an investment banking angle. I used to work on equities like the stock market and stuff like that. I had no background in credit risk. It took me like 6 to 8 months of regularly, not just reading and learning. That is obviously has to be there, but actually putting stuff up on GitHub and LinkedIn. Although it's not that I got my job because of that, right? But when I actually went in there and interviewed for a sort of a credit listing job, I knew all the jargon that they were talking about, and I could match to their conversation because I had been doing that for a while, right? And the important thing is, like, people really value not just technical skill, but actually, so a lot of stuff that I talked about today was not really the technique, but what actually goes into practical data science in especially a credit risk perspective. People value that a lot. People value people who can actually do stuff end to end, understand the business problem and deliver a solution, and not just create models, right? So generally what I think, and so I mean, I'm somebody who's like I'm a generalist, so I don't like to be boxed into something. So I'm doing credit risk now, and I'm actually left that I'm going to do something else now. But generally what actually works for me is trying to do end to end projects and putting it up on GitHub and actually sharing that with people and saying, so for credit risk, like, I have not done this, but I've built models and I've sort of deployed that and created a UI saying that if you input these parameters, I'll tell you what your credit risk is, right? So a simple website. So because the tooling has become so much better, data scientists can actually deploy end-to-end solutions now, right? And for, like, either for free or for very little money, you can actually have like a portfolio, like a model or an actor has a portfolio. A data scientist should also have a portfolio, right? And a portfolio is what will set you apart, not your resume. If you're trying to break in, that's what my thinking is. Because one, you have the portfolio, and second, you would have to put the work in to build that portfolio, right? So you'll be all the better for it.
Yeah, that's so true. And I think it's a similar trend in US as well. If you're like trying to break in, if you obviously your resume needs to be up to the mark, but portfolio kind
Yeah.
of sets you for success very soon. Great. So I think Rohan, we can conclude the session then, since we don't have any more questions. We are
Yeah,
at
of
time.
course. Yeah, of course.
Okay.
It was a great session.
Awesome. So thank you so much, Dhruv, for joining us, and thank you everyone for tuning in on a Saturday morning or evening. So thank you, and stay tuned
Thanks a
for
lot.
other DeFi and DBus data bus sessions.
Thank you.
Thanks. Bye.
Thanks, Dhruv, for joining. Thanks, Rohan.
Thanks,
Bye.
Supreet. Bye bye.